Okay, so Stuart and Jason have set the background for some of the results which I want to show you. I started on this work in 2007 when Paul took me on, and very early on Stuart appeared. We had a workshop in this room actually, I think. And that was my first introduction to Acoustic Indices. And it was the AHQI Acoustic Health Quality Index, which I notice now Stuart's renamed. But the idea was that if you made an assumption that in the low frequency portion of the spectrum you've got mostly sound is attributed to human sources, and in the higher part of the spectrum it's due to biological sources, then you can take some ratio, and that is a measure of acoustic health. And then that got me thinking, well, what other indices might be possible, because there's I think Stuart agreed, there's a problem with this particular index, and that is that of course you can have frogs and whatever at a low frequency, and you can have birds which are producing in the and you can have technological sources in the high frequency part of the spectrum, and so that can create problems for this particular ratio. So a good old engineering approach is just the signal to noise ratio, and how that applies to an acoustic landscape. This is a portion of an acoustic recording in the top. There you can see the dark red. That's a koala call. It's a real koala call. This one here is some artifact caused by mobile phone noise. So this is low frequency. This is high frequency. Time is through there, and so and through here we have a continuous cicada noise. And the way I wanted to think about this is that you can picture this as a landscape in which we have some topography. That's actually the land itself, and then dotted on the landscape we have these acoustic events like trees or forest on top of the actual land. And it would be nice to make a distinction between the background, essentially that's the noise, and the signal, that's the events which are dotted on this acoustic landscape. So there's an attempt to get at that. Stuart had already in some of his data was getting towards this kind of thing. So this is the acoustic landscape for a site near Brisbane Airport, averaged over, so it's the x-axis is midnight to midnight, averaged over 15 days in October 2007, and the top graph is the background noise, and the bottom graph is the number of acoustic events that, if you like, are dotted in this in the landscape. Near Brisbane Airport, you'll see that, probably easier at my point, we have a lot of acoustic energy in that low frequency area, and that's because there's a motorway nearby, so that's essentially reflecting motorway noise. This here, a very strong population of cicadas, and you'll notice they're temperature sensitive because the frequency increases as the temperature gets hotter. And the other thing about those is that although there are individual cicadas which are close to the microphone, there are so many of them dotted through the landscape that it becomes part of the background noise of that particular location. On the other hand, you'll see that we have a very, in the lower graph, where we're now looking at acoustic events. So this is actually things that are dotted, if you like, acoustic events that are dotted on the acoustic landscape. Very strong morning chorus and quite a strong evening chorus. And this activity through here would be birds, and this activity here is actually cicadas which are close to the microphone, which stand out as individual events. So that's an acoustic energy map for that particular location, and it's quite meaningful, as Stuart said, that you can interpret these things. If you know what's there, it makes perfect sense, so you should be able to make predictions about other landscapes. Another way of representing the number of acoustic events at the bottom right there, so it just shows you the remarkable nature of the morning and evening chorus at that particular location. So I thought, okay, hypothesis that if we wanted to compare environments, could we say that a city environment will have high intensity background noise, but be poor in acoustic events? A natural environment would have low intensity background and rich in acoustic events. and I had the good fortune to be able to compare 3 different environments. The top left is St. Bees Island, so that's a, if you like, undisturbed site. In the middle is the Brisbane Airport site, which I've just shown you, and bottom right is the Brisbane CBD, actually. Each of these graphs makes perfect sense if you understand the environment. Probably I don't need to go a lot into it. Clearly we have a form of cicada through here, which is not temperature sensitive, like this one is here, and Ian told me that's because it is a cicada which lives underground. So I think there was a species. Yeah, I remember you mentioned it once.
Did you see it?
No, I don't listen to it.
Just looking at this graph here, and bearing in mind that this is Margaret Street, and we have in the low frequency area quite a high intensity of noise around 6 and 8 in the morning, but not the equivalent in the evening. So the question is, why would that be?
It's a one-way street.
It's
Well done, Peter.
130 IQ straight up. Okay. Oh yes, okay, so this is a little bit harder question. Again, background noise. Not much in the morning here, but noticeably more background noise in the evening or the afternoon. This is a particular site. I suppose you should know that St. Bees Island, there's a clue.
Jet skis?
I don't think so.
I was going to say coastal winds always pick up in the afternoon.
Yeah, it's coastal winds, yeah.
And then
So,
off at midnight or 2 a.m.
Yeah.
So that's just to give you the sense that these diagrams are interpretable and they make good sense. The only other thing I want to point out from these is that as far as the hypothesis is concerned about the city, well, rich in noise or high intensity background noise and poor in acoustic events compared to this landscape, but actually St. Bees is surprisingly, I expected more. It's there, the birds are thin. These are averages over 15 days in each case, so the averages tend to smooth things out. So what you're seeing in these graphs is only what's persistent day after day after day. So it's a statistic. Like all statistics, it hides the detail.
So when you say poor in acoustic events, the diversity of them, the diversity of the frequencies. Is that what you're saying?
Poor in acoustic events means that, on average, there's less happening at this site than there is at this site.
Okay.
I think that it's again, like all statistics, they only make any sense when you compare them. So uses of acoustic indices, what we've been talking about is in acoustic indices in terms of health, acoustic signatures, that's the word I was looking for, and you could have a benchmark site or reference site, and one can see how this could contribute to the habitat hectares and habitat condition measures of environmental health. Okay. We can use these indices to detect non-biological events, and some of this work has been done in Makuta, detecting rain, wind, thunder events. Why would you want to do that? Because these recorders, you can hide them under the undergrowth in the bush somewhere, whereas if you leave a weather station out in the open in a public place, it's probably going to get damaged. So we can, and it's useful to know when it's raining because you can cut a lot of that out, and also, well, for example, if frogs are calling after rain, then it's good to know when the rain is. So that's second use. And finally, I want to talk about another use for acoustic indices, and this is what Jason has set the background for, is smart sampling and very long recordings. So as Jason made quite clear, you can't possibly listen to 3 weeks continuous recording, and that's the sort of thing we're getting. So there just has to be some way of sampling that intelligently to get the maximum leverage from those recordings. And one could imagine sampling for different reasons, like you want to give samples to birders, or you want to give samples for citizen science tagging, or whatever it might be, the project you've got. So this is what I've been doing for the last few weeks, and this is a graph of the data which Jason's got. He showed you several days of this. This is just one day, I think 13th of October last year, and that's 24 hours of recording, broken into minute chunks, and for each minute the taggers have counted the number of unique bird calls in that minute, and that's what the profile looks like over the day. And so the question is, well, how can we identify the most species with the least number of samples? And you can see why dawn plus 3 hours is a good choice, because that gives you this portion here, where you most likely have the most different species. So what I did was to extract for each one of those minute recordings 13 indices, and those plotted in these tracks here. So this is midnight to midnight, and to give you an idea how this is working, the bottom track here is the species count. So that previous graph which I showed you, the intensity of this black line here is the proportional to the height of the line. So this is the morning chorus here, and then this is nighttime here, there's no activity.
So is there anything that gives us an idea about the variation of the species, Mike? Because that's the trick, isn't it? That's what we're after, really.
Yes, I can, if I try and go through all of these indices, you'll probably get bored too quickly. A couple of things, okay, some things I'll point out. This third track here is the signal to noise ratio, this one through here. So that's what I was attempting to plot in those other graphs I showed you before. The signal to noise ratio is high at the morning chorus, and then there will be particular places through here. And this is not particularly informative, the signal to noise ratio, simply because it depends upon whether some bird is squawking close to the microphone or not. So I'm not telling you anything deep about the particular location. This one's interesting here. You'll notice that we have this intense activity, acoustic activity here, and that marks the end of the day's activity for the birds. This is the bird counts through here. And that's a cicada chorus, which pretty much terminates the day. What you'll see here is that most of these indices have low values during the night. In other words, there's not much acoustic energy, and most of these indices are related to acoustic energy. But we have a 3 here, which is the reverse, and these are measures of entropy. That's the statistic. They're measures of entropy. You understand entropy in this context as the degree of dispersal of the acoustic energy either through time or through the spectrum. So high dispersal of energy, of acoustic energy, will give you this black line, and low dispersal, concentration of acoustic energy in particular cores or at particular times or in the spectrum, is low entropy. So as we would expect, we have high entropy at night and less during the day. But you'll notice during this cicada chorus, because it so dominates the landscape, the acoustic energy is very intense, but it's very dispersed, so we have high entropy here as well. The question which Paul asked about, is there any measure of the diversity of the different spectral types in the landscape, acoustic landscape, and that's what I've attempted to capture in this third from the bottom, this one through here, and it seemed to be pretty good. Obviously we've got, so this is the number of different spectral types, how the spectrum varies in that minute, and we have lots of spectral variation through here and not much at night. So anyway, we've got 13 indices, and the trick was to see, can we use these indices to direct our sampling of very long recordings so that we're starting to pick up places where we're likely to get bird calls. That's the point of all of that. Okay, so just to give you an example of how we might use this information, on the left-hand side we've got that same graph of the number of species counts. On the right-hand side, in this case, is that entropy track, and you'll see entropy is high at night and low in the day as a measure of dispersal of the acoustic energy. You plot those two together, and you'll see that, okay, you fit a line through there, the exponential decay. It's got an R-squared value of about 0.5, and I think that's bad. Ian seems to think that's not so bad. I'll stay out of it.
N equals...
N equals 1400, that's quite healthy. The point is that just to fine simple relationship between these indices and species count is not going to work. But can we use this information nevertheless to guide sampling? Can we get some leverage from that? And the answer is we can. So coming back to the problem again, how to detect the most different bird species with the minimum effort. And so let's just concentrate on the getting 75%. S25, S50, S75 means the number of samples required to get 50% of the identified species. So it's like a t-half value for radioactive K. It's the amount of time, so it's the number of samples to get 50% of species. And so let's forget 100%. Jason thinks that we should be going for 75%, and that's that's not a bad deal. So this is the same graph, and because we can repeat random sampling many times, we can get some sense of the standard deviation for what you might expect sampling many times. And so this is the best possible deal. This is what I think is a good benchmark. And then this is the informed sampling strategy, where you sample only at sunrise. The difference being that if you only sample 3 hours after sunrise, you can never get 100% of the species, whereas you obviously can if you use some other strategy. So the question is, can we do better than this informed sampling strategy where you sample at sunrise plus 3 hours? Using the indices, which I showed you before.
So, let me check I understood. So that's saying that I can take 100 1-minute samples randomly plus around sunrise and I'll get 75% of the species?
On average, yeah.
On average. Yeah. I mean, that's pretty good. That's sort of 2 hours, isn't it? Still, that's better than the birdos are doing, right? The same amount.
Yes, well, that's the point that Jason was making. Yeah. But the question is, it's still random sampling. Can we use the indices to do better than that? That's what I'm getting at. And the last graph, I think it's the last graph, essentially the answer is, well, yes, we can do better. So this is the benchmark, random sampling over 24 hours. This is the sampling randomly 3 hours after sunrise, and taking just one of the best indices which I found, simply ranking the 1-minute samples by the value of that index and sampling in that order, and it's the number of active segments. So what you do is you're just essentially you're counting the number of acoustic events in the 1 minute, and if you just do something simple like that, you can already, to get 75% of the species present, you've already cut your sampling down from 100 to 47. Now, if you do something else, which is instead of just relying upon one of those indices to guide your sampling, you start to take some weighted combination of those indices. Then, and I just played around yesterday for some time, and the best I got down to was 32. So essentially what we're down to now is, in theory, 32 samples will get you 75%. That's half an hour's work. Well, sorry, it's listening to well, if you take 30 samples, but then of course you've got to listen to them all. Yeah. Okay. So essentially, okay, let's put it this way: that with smart sampling, you only need to listen to half an hour of recordings in order to get 75% of the species present. Now, where this is going is that this is an optimization problem. In other words, it's just essentially how do I weight these indices, and there are a few other parameters thrown in there where you've got to try and find some optimum value. So let's say you've got 10 parameters to optimize, and so this can now go very fast because all the information is stored in the database, and I think we could possibly get this down to say 20 samples. But the one catch is that by the time you start to optimize your sampling regime for this particular 24 hours of data, there's no guarantee that the same combinations and the same weights parameters is going to apply for the next day. So the next step is to get another day's data, another 2 days' data, optimize the parameters on day 1, and then test it on days 2 and days 3. And then you've got but my guess is, just from working with the sort of training test data before that we could perhaps optimise on a particular day, get down to 20 samples, but when you go to another day, you're probably back up to 30 or 40. And at the moment, using the indices we've got, it's probably about what we'll manage. But that's not to say that there aren't other indices and other tricks that, that I could try. I mean, there's ideas, it's just they all take time to implement. And I think that's it.
That's very cool.